Okay, so let's go ahead and get started. Good morning, good afternoon, and good evening to all our esteemed customers joining us from around the world. Hello, everyone. My name is Lokesh Chorara, and I'm one of the managers for the Arista Technical Services team. And on behalf of the entire team, I extend a warm welcome to each and every one of you to this remarkable webinar series graciously hosted by the Arista TAC team. For those of you who are joining us for the first time, allow me to provide a brief overview of this initiative. Through these webinar sessions, our primary objective is to foster knowledge sharing with our valued customers, focusing on comprehensive and practical topics which are utmost importance to everyone. We embarked on this endeavor in 2022, covering essential topics such as switch, health checks, upgrades, and maintenance planning. And now in 2023, we are thrilled to continue our journey, delving into more advanced technical topics. So if you wish to visit any of our previous sessions, including the presentation materials, they are accessible on our community page. In the 2023 series, we actually dedicated our first quarter to exploring a typical layer 2 and layer 3 setup debugging. Throughout these sessions, we actually did a deep dive into numerous practical use cases and valuable commands that prove instrumental in troubleshooting such environments. And in Q2 23, we are shifting our focus and moving on to a more complex topic, which we did receive a lot of demand, that is VxLAN. And recognizing the vastness of this topic, we have carefully structured our Q2 series into 3 distinct sessions to provide a comprehensive coverage. In our previous April session, we focused on VxLAN bridging setup, and now today, we actually are going to do a deep dive into VxLAN routing environments. Our next session is going to be in June. It's also going to be a continuation of this topic, where we are going to extend the use case to even more complex scenarios. So coming back to today's session, we actually created a lab topology based on our customer interactions, and we actually will be navigating through this topology and highlighting the debugging approach. To all our registered customers, we did send out this topology proactively on 26th of May. And our speakers will be highlighting this topology in between the debug scenarios, but it'll be a good idea to take a snapshot of this topology and keep it up on your screen for reference. We do have a PDF download link available in the QA sections, which our panelists are putting now. So again, the request is to download this and keep it handy during the course of this presentation. A little bit about the webinar schedule in 2023. After today's session, we have one more session planned for VxLAN in June. And after that, we are going to take a short break in July and resume in August for 3 more sessions on EVPN. So today, we are delighted to have 2 of our exceptional engineers joining us, who will be guiding us through this session with their expertise and insights. Firstly, we have Diego Serrano Mendes, who will expertly navigate us through the CLI component to debug VxLAN routing. Following Diego, we will have Grant Bonds, who will delve into the CloudVision side of presentation, showcasing CloudVision's capabilities and demonstrating how it can enhance your VxLAN experience. Again, this session will be recorded like the previous sessions, and it'll be made available on the Arista Community Central if you would like to have access to these in the future. Along with the presenters, we also have our technical leads as part of the panel who can help answer any questions what you may have during the course of the presentation. And we highly encourage you to use the Q&A manager to ask our panelists any question during the course of this webinar. So without taking any further time, I'll hand it off to Diogo for taking you through the CLI part. Diogo, take it away.
Okay, thanks, Lokesh, and hi, everyone. My name is Diogo Mendes, and I'm a tech lead here in Arista TAC. And today, as mentioned by Lokesh, I'll be covering how to debug traffic flows in a VxLAN routing environment. This is going to be the first part of this subject, and then the second part will be covered in the upcoming webinar session. So for the presentation today, I will start with a brief introduction to VxLAN routing. Then I'll be providing an overview of the scenarios we have and with some of the common issues we see in the field. And throughout the session, we're going to be guiding you through how to leverage EOS CLI commands and tools, and also Cloud Vision Portal in order to help us debugging issues related to this VxLAN environment, with routing also being part of it. So before we deep dive into the scenarios we have for today, I just wanted to take a couple of minutes to make sure we are on the same page when we talk about what VxLAN routing actually means, right? Because VxLAN as a protocol itself, it's gonna essentially just encapsulate the frames into IP UDP packets, and this will allow us to tunnel these frames across different layer 3 domains. But there is no real built-in routing concept as part of VxLAN as a protocol. So when we talk about VxLAN routing, we are essentially meaning that we are somehow integrating the routing capability into this environment. So in our context, since we are talking about VxLAN, we have our switches which are capable of performing layer 2 functionality, VxLAN encapsulation, decapsulation. So they are called VTEPs, VxLAN tunnel endpoints. And they're also, on top of that, also capable of performing routing. So the way we enable this is very simple. It's just by creating SVIs as part of the VxLAN enable VLANs. And we have here a very simple example just to make it a little bit more visual. So essentially, you're going to have the original frame coming as part of a segment. Destination is located in a different segment. The switch here is not only a layer 2 switch, a VTEP, but is also equipped with an SVI on both segments here. So it's capable of performing routing. And then since the destination will be located, connected to a remote VTEP, there will be VxLAN encapsulation being performed, and the packet will be sent over the underlay network up to the remote VTEP. And apart from having the SVI, since we're going to have SVIs potentially on all VTEPs, or at least a subset of them, we also need to configure a concept of Anycast gateway. So Anycast gateway is essentially going to be the gateway for the hosts within the VxLAN fabric, and this is going to be shared by many VTEPs throughout the network. And the way we configure that is essentially just by specifying a virtual IP and also a virtual MAC. The virtual IP can be configured with different methods. The first one here is the command IP virtual router address under the SVI. But we also have another option, which is the IP address virtual command. There are a few differences between them. We're not going to deep dive into them today, but we are definitely going to cover that in more details in the upcoming session. In case you're curious to know a little bit more on that, the second link shared in this slide provides a comparison between those two. We are going to be adopting just IP address virtual for the scenario today, as this is a very common deployment in our customers nowadays, and it has been, it's a command that has been designed specifically for VxLAN environments. So that's actually one of the most important points to highlight. This is going to be supported only for SVIs in a VxLAN enabled VLAN. And the virtual MAC, as I mentioned, this is pretty straightforward. No matter which option you choose for the virtual IP, virtual MAC will always be configured in the same way. Just go to the global configuration mode and use the IP virtual router MAC command, and you specify what the virtual MAC is. The other link that I shared is also a very good article that covers essentially an overview on VxLAN routing, and actually a lot of things that we are discussing today are part of this document. So definitely a good resource for you to review along with this session. So now let's take a look into our topology diagram here. What we have for today is essentially, just a basic spine and leaf design, layer 3 spine and leaf. So this means that the links between spine switches and leaves, they are routed ports, layer 3 links, and we have all the leaf switches configured as VTEPs. So they are capable of doing VxLAN encapsulation or decapsulation. And each one of those VTEPs also have hosts attached to them. And we have hosts in different subnets, so we can simulate different flows routed flows between networks, different networks in different segments. In terms of hardware support, we have a mix of platforms, starting from R3, also having R2 and X3 series. All of them are going to be running the same software version here for consistency. So we have EOS 428.3M being used. So now, since we are now familiar with the topology diagram, let's take a closer look here on the first problem statement. So essentially, this problem has been reported, and the main symptom observed is the fact that is excessive traffic flooding going across the VxLAN fabric. And this has been observed to be intermittent behavior. So it's not always that this is happening, but this is happening pretty frequently throughout the day. We are going to be focusing on one particular flow here between host 1 and host 2. So host 1 is part of VLAN 10, VNI 1010, and host 2 is part of VLAN 20, VNI 2020. And these are going to be essentially VLAN 10 is supporting subnet 10.0.0.0/24, and VLAN 20 is having the subnet 20.0.0.0/24. And by the way, I also added here the link for general health checks that you can also review. This is essentially the previous session we had, where we discussed how to debug traffic flows in a VxLAN environment without routing. So it was more focused in overall VxLAN related problems, but definitely those two sessions will be very useful to be reviewed together. So we're going to have an overlap of some of the content we're going to review today, and also we're going to try to find also focus on some of the things that are more specific to VxLAN routing environments. So with that, let me go through our lab demonstration that we have for today. So skipping forward here, we have the first device here that we are gonna examine is VTEP 3. So I will keep the topology diagram here as much as possible so you can follow along and have a better understanding of where we are. And I will also have some labels for the VTEPs and other hosts and devices that we are accessing. So I will start by going through VTEP 3, and my intention here is just to make sure that we are indeed seeing the intermittent issue at the moment, right? Because otherwise it's going to be difficult for us to correlate the output with the actual symptoms. So I'll do that by leveraging the port mirroring feature that is configured by using this monitor session. So you can see that I have a previously configured monitor session called underlay. You can check that by using the show monitor session and the name of the session. And what this session is doing is essentially just mirroring the traffic that is going through the interfaces here between the VTEP 3 and the underlay network. And it's sending a copy of this traffic to the CPU of the switch itself. So this will help us to have more visibility over the traffic that is going through the switch. So this is the traffic that is being forwarded at the ASIC level. So without port mirroring, you would see only data plane, only control and management plane. And now we're going to also be able to see the actual data plane. So the way we can do it is just by using TCP dump, specifying the name of the monitor session. And in this case, I'll also use a filter just to filter only VxLAN encapsulated packets. And once we take a closer look here, we do see traffic that is coming from VTEP 1. We can tell by the outer header. The source IP is the VTEP IP of VTEP 1. And we can see the inner header. We can identify this as a ICMP echo request, and is being generated by host 1. And we also see traffic coming from VTEP 2, and it's coming to our VTEP IP. And the inner header shows that this is the reply from host 2 to host 1. So we are indeed seeing this traffic that ideally, based on your topology here, it seems to be unicast traffic. So we would expect this traffic to be only going through VTEP 1, one of the spines, and VTEP 2. But we are also seeing this in VTEP 3. So since we are seeing both directions of the traffic coming from VTEP 1 and 2, being flooded, next thing we're going to do is to go into their SSH session here. And we're going to see that I personally really like to start with the show version output, because regardless of the actual problem you're troubleshooting, it will provide us very important details about the environment. So the first thing that I would highlight is the actual hardware model. So we have those two VTEPs are 7280 SR2 devices. And the other very important point to highlight is the software image version. As we already discussed, both are running for 28.3, but that's probably the best thing you can do once you start troubleshooting session, no matter what the issue you're troubleshooting, because based on that, especially this combination between hardware and software, some features may or may not be supported, or even if they are supported, there could be some caveats or specific requirements that are pertinent to that particular combination. So VxLAN routing is actually a good example of that. For this switch model, we actually require, apart from the SVI and the Anycast gateway config, we require what we call a hardware TCAM profile. We can check that by using the show hardware TCAM profile command. And we can see here that we do have hardware TCAM profile configured. Otherwise, it would appear here as default. And we have the TCAM profile called VxLAN-routing. So this seems to be properly configured, and it's especially important detail because without this TCAM profile, the VxLAN routing feature won't work properly. And you can look at more details about this in your EOS configuration guide. I have the link here and also part of the page where this is explained in more details. There are other platforms that may require also some additional configuration. So definitely would recommend to take a look into not only the configuration guide, but also the TOIs available on Arista's website. So I guess in this case, we are seeing that this is properly configured. I like to start with that because otherwise you might deep dive into more complex troubleshooting, but you're missing something very basic, such as the VxLAN TCAM profile. Next thing we're going to do is to try to be more specific here on our investigation. And since the main symptom we are observing is traffic being flooded to other VTEPs, and this seems to be unicast traffic, we can look into the show interface VxLAN 1 output. And there are a few things here that are very helpful for us. So the first one is just the VTEP IP. So we can confirm these are indeed the IPs we saw as source in the outer header of the packets. There is this detail here, virtual VTEP IP address. I'm not going to go into details right now, but this is going to be covered later on this presentation. But just for you to have an idea, in case you're not familiar with this concept, this is also a requirement when you have VxLAN routing distributed among different VTEPs in the network. All the layer 3 VTEPs are supposed to share this virtual VTEP IP. But we're going to go back to that later on in the second issue. For now, I'm going to focus especially on this line here, where we see the replication flood mode, and it says is head-end with flood list source CLI. So the replication flood mode here is just means that every time there is traffic part of VxLAN enabled VLAN that needs a special treatment, needs to be forwarded. It's not just regular unicast traffic. It's boom traffic. Boom traffic stands for broadcast, unknown unicast, and multicast. So every time you have some sort of boom traffic in these VxLAN enabled VLANs, not only this needs to be forwarded locally here in the switch, but it will also need to be replicated to all other VTEPs in the network that are interested in receiving traffic for that subnet, right? For that segment, to be more specific. So this is how the VTEP will know how to, to where this type of traffic needs to be replicated to. And the way we're gonna determine that, in this case, is through CLI. So this just means that there is a stat configuration done through CLI, where we are setting this list here of remote destinations as part of the flood list. This could be in some deployments. We have, for example, EVPN being used in order to populate this flood list. So this can be done in different ways, but for our scenario today, we're going to use just regular stat configuration through the CLI. The other problem, well, not a problem actually, but the other very important points to review that might be related to our problem is this next line here where we see the remote MAC learning. It says it's via data path. So this just means that for the VTEP to learn MAC addresses that are behind other VTEPs in the network, it will rely on essentially flood and learn, right? So the VTEP, once it received some traffic, with the source MAC being a MAC address of a host, for example, one of the hosts connected to the remote VTEPs, it will learn this MAC address and will add to the VxLAN address table and also its own MAC address table. So this could also be done through different methods such as EVPN, but in this deployment, we are just using regular flood and learn, similar to regular layer 2 network. Apart from that, we are also seeing here that we do have the VLAN to VNI mapping. So VLAN 10 and 20 are indeed VxLAN enabled VLANs, and the mappings are consistent. And so this is definitely required. So otherwise, we wouldn't have these segments properly extended. So at this point, what we noticed so far is that we have flooding. This flooding doesn't seem to be based on our previous packet analysis. It doesn't seem to be broadcast or multicast. So it's just unicast traffic. So we can safely assume this is unknown unicast flooding. And the way we can check if this is indeed the case is basically just checking the MAC address table of VTEP1 and also VTEP2. Can just use the show MAC address table command. And here we see that we have a couple of MAC addresses on both sides. So let's first look into VTEP1. And in VTEP1, we do have a MAC address that is learned from a local interface here, Ethernet 7, and this is the port towards the host. So we see MAC address 8A59 being learned from this port. So this seems to be the correct behavior here. We see that this is where the host is connected to. But then we have another MAC address here, which is 971B, but we don't really have the MAC address of host 2. In VTEP2, we see something similar. Locally, we see the MAC address of host 2 being learned. So it's 4A89. And we do see a MAC address being learned through VxLAN, which is 9A93. But again, we don't see host 2 MAC address on VTEP1, and we don't see host 1 MAC address being learned in VTEP2. So that's indeed the case. We are seeing unknown unicast flooding since the switches here don't have the MAC address of the host connected to the remote VTEP. We can also take a look on the VxLAN address table, and it's pretty much the same information plus the information about what is the actual VTEP from where this MAC come from. And in this case, we can confirm this is indeed learned, the one from VTEP2. We can see this is coming from VTEP1, and the other way around is also true. So at this point, what we can do here since we are relying on flood and learn, the best thing we can do is to actually try to identify whether or not we are receiving traffic with the source MAC of the hosts, so we can ensure that those MAC addresses are learned properly by the switches. And we are going to do that by using, again, a monitor session. So you see that apart from the monitor session called underlay, I also have another one called overlay. And this is just mirroring the traffic here of the interface, going through the interface towards the host. And I can, again, use the same methods using TCP dump. And by using TCP dump and using the name of the monitor session, I'll be able to capture the traffic, data plane traffic. If we look into closely into the traffic that I captured from VTEP1, we do see echo request and reply. And the echo request here, we can see that the source MAC is 8959. Sorry, yeah, 8A59. So this is the MAC address that we expect from the host. And that's why we are actually learning this MAC address locally. So this seems to be okay. The destination MAC is our virtual MAC. And again, this is expected as this traffic is towards hosts within a different layer 3 network. So this needs to be sent to our gateway, which in this case is the Anycast configured on some of the VTEPs. So this part is fine. But then when we see the traffic coming back, we can notice interesting things here. So you see that the actual MAC address here is the MAC address 971B, the source MAC address that we see from the ARP reply, the ICMP echo reply. And the destination is the MAC address of the host. So that's why we do see this MAC address being learned from the remote VTEP, because this comes as the source MAC address, but we don't see this coming with the MAC address of the host. So in this case, if you don't have this traffic coming with the MAC address of the host, this MAC address won't be learned. So the next step is going to be to do something similar, but now I will move one step further and I'll use the underlay monitor session. And I want to see how the traffic looks like after this has gone through VTEP 1, and then before this is sent out towards the underlay and the remote VTEP. And looking closely here, the packet capture, I can notice a few things. One of them is that we do have indeed traffic being flooded. You can see the echo request. You can see multiple copies sent to each one of the remote VTEPs. But more importantly, I can also see that now, if you look into the inner header, the source MAC here is 9A93. So this used to be the MAC address of the host, but now it's being rewritten to 9A93. And this is exactly the MAC address that VTEP2 learns. And it makes sense, since when the traffic arrives at VTEP2, this is the source MAC. And if you look at the echo reply, we see something similar. Again, same thing. We see the MAC address 971B, and the destination is the MAC of the host, but MAC of the host is not learned since we don't see traffic coming from it. So at this point, I think we are probably, you guys already suspect what is going on here. So if you look at the VTEPs, both of them here, you can see that they are configured with the SVIs for both VLANs, and they have also the Anycast gateway configuration. So this means that they are what we call L3 VTEPs or routing VTEPs. So they have the Anycast, the virtual IP, and the virtual MAC configured. So they are effectively able to perform routing once they get packets that need to be routed. So this means that if you look closely here, and just to be a little bit more visual, I have this topology here. What we saw so far from the captures is that initially we have the MAC address, source MAC address as the host MAC, but then once it gets to VTEP 1 for the ICMP echo request, VTEP 1 is a layer 3 VTEP, and is gonna perform the routing operation. And this is performed locally here, since we have both SVIs. This is routed, MAC addresses are rewritten, and now the source MAC address will be VTEP 1, and destination is going to be VTEP, host 2. This is going to be VxLAN encapsulated, send it to the underlay, and finally arrive at the other VTEP. In fact, it's going to be flooded since we don't have the MAC address of the destination learned, but more specifically, we are interested in what is going to happen once the traffic gets to VTEP2. So once this arrives, the packet will be decapsulated and sent over to host 2. We have the MAC address of host 2 on this side of the network. So this is going to be delivered to host 2, which is going to reply with the echo reply. But again, something very similar is going to happen. Initially, the source MAC address will be host 2. The traffic will arrive at VTEP 2 that is going to perform routing operation first, and then rewriting the source and destination MAC addresses. And again, once this traffic goes towards the remote VTEP, the source is now VTEP2 MAC address. As we can see, even from the show interface, VLAN 10 and 20, these are essentially the MAC addresses of the SVIs. It's the system MAC address of each one of the VTEPs. So essentially what you're seeing is the fact that it's not a problem per se. I mean, in terms of the function of the devices, devices are actually operating pretty much as they should. The problem is now just the fact that the traffic flow, the traffic pattern we have, plus the design with this asymmetric routing with Anycast gateway, this ends up causing this situation where the MAC addresses of the hosts won't be learned. But then we can try to, based on that, we can try to understand why this wasn't actually a problem in the beginning and why we see the problem intermittently. So the answer for that is essentially, if you look at how the network looked like at the beginning, right? At the beginning, there was no ARP and MAC addresses learned. So what happened is that host 1 sent the traffic towards VTEP 1. VTEP 1 performed the routing operation. But since the MAC address and the ARP entries weren't known, this triggered, VTEP 1 triggered ARP request. This ARP request is a broadcast message, was VxLAN encapsulated, sent to all remote VTEPs part of the flood list, including VTEP 2. VTEP 2 received this traffic. Once this traffic was received by VTEP 2, VTEP 2 learned the MAC address of the source MAC address of VTEP 1. Then it sent the traffic, replicate the traffic here, flooded through all local ports within the same segment, including Ethernet 5, where host 2 is connected. Then host 2 replied back, and with its MAC address, so we have the ARP reply coming from host 2, and the source MAC is host 2 MAC addresses, right? So once this traffic arrives at the VTEP 2 will already know where the destination MAC is. So in this case, it's going to be the other way around. So the destination MAC will be MAC address of VTEP 1, and this traffic will be delivered back to VTEP 1. And this is when the key point of our discussion happens. So due to these ARP requests coming from the VTEP that is operating as a router, and the fact that the host replied back with this ARP reply with itself, its own MAC address as source, this triggered not only the ARP learning from the perspective of the VTEP here, but also the MAC address learning, because in this case, differently from the echo request and echo replies, in this case, there was no MAC address rewritten. So we have this MAC address coming to VTEP 1, and VTEP 1 will learn the entry for the host. And the same thing is going to happen the other way around. I'm not going to go through everything once again because it's redundant, but essentially the same thing will happen with host 1 and VTEP 2. So essentially, again, as I mentioned, there is no actual problem with the devices per se. It's just a matter of how the default behavior works. But we can definitely adjust that, and I'll show you how. Well, first of all, just to give you an explanation here, we have a different setup. On the top, I have VTEP 3, and I have the TCP dump running using monitor session underlay. Then I have also running VTEP 1 here in the middle of the screen, VTEP 1 in the left-hand side, VTEP 2 in the right-hand side, and both of them are also running TCP dump. And I have actually 2 sessions in the bottom of the screen. You can see another session with VTEP 1 and 2. And in this one, I'll be typing some commands so we can better understand the scenario. So if we take a look into the default configuration for the devices, right? So we have this show bridge MAC address table aging timeout command, and this will essentially show us the MAC aging time that is configured at the moment. And so we can see we have 300 seconds, which is 5 minutes. So this is essentially the reason why we do learn the MAC address at the beginning. However, after this timer expires, after 5 minutes, the MAC address goes away because we don't have any other traffic with source MAC of the hosts. And this ends up being a problem here because if you look at the show ARP VRFA, because those are part of VRFA, if you look at the ARP cache, we do have the ARP entries here. So in terms of layer 3, we need the combination or the mapping between IP and MAC address, and we do have that. That's why the layer 3 communication actually works, but we still see the flooding, which is an undesirable behavior. from the layer 2 perspective, right? And this is because of this discrepancy between the ARP timeout and the MAC aging time. If we didn't have this asymmetric behavior, this wouldn't be a problem. So this is not always a problem. But in this case, the combination of the design, the layer 3, plus the default timers, then we end up having problems. So if you look a little bit further here, we have, we can actually simulate what happened, the second scenario that I described with the MAC learning being triggered by the ARP learning. And we're going to do that by clearing the ARP for the entry. So in VTEP 1, I will clear the ARP entry for host 2. And you see that once I did that, ARP request has been generated by VTEP 1, and we get an ARP reply coming from host 2 with its MAC address. So this is what we were expecting. And you see that we already don't see the ICMP echo request being flooded anymore. So this fixed our flooding issue. And we can confirm that by looking at again to the ARP cache, and we see that now we have not only the ARP, but also the MAC address entry. And same thing, if you look at the show VxLAN address table, we do see MAC address of the host there. We can do the same thing on VTEP 2. So again, we are missing the MAC address entry, even though we have the ARP. If you clear the ARP for host 1, ARP request is generated, ARP reply is sent back, and due to this process, we end up learning the MAC address. So now we do have MAC address learned in the VxLAN address table. We can monitor that, and if you monitor for long enough, by the way, I'm speeding up here our session or video just for the sake of the time. And you see that after 5 minutes, we lost that MAC address entry, and we start seeing flooding once again. And after a little bit more, we also lost the other entry in the VTEP 2 as well. So now we see the flooding coming back. So that's why, of course, I managed to, let's say, work around the situation by clearing the ARP and triggering this ARP reply from the host sides. But after 5 minutes, we still have the same issue. So the way we can fix that, again, we can confirm that this is expected due to the aging timeout that is configured by default. But in order to permanently fix this and not have this intermittent behavior, we can essentially just adjust the timers. So I'm going to adjust the MAC address aging time using this command from the global configuration mode. And for the sake of the demonstration, I'll set to a very low value. For sure, this might be too aggressive for production environments, but for our demonstration here, I just set as 40 seconds. And I'll do something similar for the ARP timeouts. And this can be actually adjusted globally or just within the VLANs that you are interested in. In this case, I'm just going to change for VLAN 10 and 20, but you could do this for any SVI. And you can just do that by using show ARP aging timeouts, 30 seconds in this case. The idea is that this needs to be lower than the MAC aging time. So you can have the MAC address, you can have the ARP being refreshed, as we can see here from the traffic captures. We see that both VTEPs send a new ARP request and got a new ARP reply once we changed the timer. And then what you can see this from the ARP cache is that we do have the ARP and the MAC address learned. And again, if we monitor that long enough, in this case, up to 30 seconds, you're going to see that in the 30 seconds, we are going to have ARP being refreshed. And this helps to refresh also the MAC address entries for the hosts. So now there is no flooding happening since we do have ARP and MAC address for everyone. So in summary, the problem here is that we have this asymmetric routing design where the layer 3 VTEP closest to the source will be performing routing before encapsulating it and sending to the destination VTEP. So as part of the routing process, we do expect the MAC addresses to be rewrite. And this is what happens. But due to the fact that now the source MAC is the SVI MAC of the VTEPs, and we are relying on flood and learn to learn the MAC addresses of the hosts, we now don't see these MAC addresses being refreshed, because the data plane traffic is just going to have the SVI MAC address as source. And as we saw in the lab, in order to prevent that, the solution is pretty straightforward. You just need to adjust the MAC and ARP timers. So the ARP timer, the ARP timeout is lower than the MAC aging time. So this will trigger this, let's say, proactive ARP request from the layer 3 VTEP, and then we are going to get the ARP reply triggering the MAC address learning. And in terms of recommendations, there is no one-fits-all type of recommendation. It really depends on your environment. But for sure, you're going to try to find a compromise between lowering the ARP timeout and increasing the MAC aging time. If you want, you can definitely discuss that with the account team, and the Arista Sync engineer will probably be able to provide some guidance in regards to that. Okay, so some notes before we move forward to the next problem. Just wanted to highlight a few things to keep in mind. So the first one is always good for us to confirm the behavior, performing tests and utilizing the CLI resources, not only show commands, but also traffic captures, monitor sessions, things like that. Because again, if we try to start troubleshooting without actually confirming the problem is in place, then you're going to have a very inefficient troubleshooting, right? And it's going to be difficult to correlate the problems with what you are seeing. The second thing is to look for patterns that can be associated with known behaviors. So at the end of the day, we didn't see an actual problem or misbehavior of the device, but we understood that this pattern of having flooded traffic from time to time, it could be most likely due to unknown unicast flooding, and we already suspect of some potential problems or behaviors. So we can create our theory and follow it to have a more structured way of troubleshooting. Then the other thing is to understand the traffic flow and perform the packet walkthrough. So that's exactly what we did. We used the packet captures and we had to, especially because we are relying on flood and learn. So this was crucial for us to understand how the packet headers look like at certain point in time in a certain part of the network. So that's also very useful. And in terms of common symptoms from the data plane, exactly what we saw, flooded traffic in different parts of the network where ideally they shouldn't be. And we can also see, especially in production networks, situations where there is congestion and potentially packet loss, depending on the amount of traffic that is being flooded. And from the control plane is even more obvious, I would say, just the fact that you have the ARP entry, but MAC address entry is missing, then it's a pretty clear indication that you might have this situation ongoing. And in terms of best practice, I would highlight always, try to review the documentation and ensure that all the best practices documented are applied. And in this case, just adjusting the MAC and the ARP times. And so we are gonna, by doing that, you're gonna avoid this unnecessary flooding. Okay, so at this point, I will move forward to problem 2. And in this case, we have a problem that affects the communication between hosts that are attached to a new pod, a new VTEP that has been integrated to the network. And those hosts are capable of establishing connectivity with other hosts connected to remote VTEPs, but only within the same segment. So it's essentially a routing problem where different subnets cannot be reached by these hosts connected to the new VTEP. We are going to be focusing on this particular flow, host 1, which is part of network 10.0.0.0/24, and host 4, which is 20.0.0.0.4, connected to VTEP 4, which is the new VTEP we have in the network. So going through our lab here, our environment, we have the remote VTEPs, VTEP 1, 2, and 3 in the left-hand side, and then VTEP 4 and host 4 in the right-hand side. Not always we have access to the host, but it's also always good to keep in mind some base verification on the host side, since this could be easily a misconfiguration. Of course, if you have multiple hosts, it's less likely to be the host side, but it's still important to know what to check and how to test things. So we're going to start exactly by host 4, and we're going to start by pinging 20002. And as we can see, the ping is successful. And this is essentially just host 2 that is attached to VTEP 2. So it's a remote host in a remote VTEP, but it's the same subnet, the same segment. So this seems to be working just fine. Next step is to try to replicate the issue by pinging a host in a different network. And indeed, in this case, we see the ping failed. So my first suspicious would be, potentially whether or not the host has a default route or the default route is correct. And we can use the IP route command on Linux, and we'll see that we do have default gateway configured, and this IP is the Anycast IP that is expected to be the gateway for all the hosts within this segment. So this seems to be fine in terms of config. So if you look further here, we can, next step, just check whether or not we have connectivity to our gateway. And at this point, looking at the ARP cache, it doesn't seem like we know the actual MAC address of our gateway. So if we jump into VTEP 4, we can use again a monitor session, TCP dump for a monitor session. I'll monitor session, use monitor session overlay, and I'll try to ping once again. And as a result, we see that we do have broadcast messages arriving at VTEP 4. So it looks like there should be, in terms of layer 2 communication between those guys, this should be fine. So next step we would expect is to have some ARP reply with the VMAC, the virtual MAC that is associated with the virtual IP. And we can check from VTEP 4 perspective whether or not this is configured. But as you can see, VTEP 4 actually doesn't have SVI for VLAN 10 or VLAN 20. So this is not necessarily a problem, actually. It's a completely supported type of deployment. There are cases where some of the VTEPs in the network could just perform VxLAN bridging, so they are not going to do routing at all. But what needs to happen then is that VTEP 4, being a layer 2 only VTEP, needs to send this broadcast message to some of the remote VTEPs that are capable of routing. So next thing we're going to check is whether or not VTEP 4 actually has the correct replication list. So we can take a look on show VxLAN floods VTEP. And here we can see that we do have the remote VTEP IPs, VTEP 1, 2, and 3. We also have our own IP, which is fine. And we have also the virtual VTEP IP. So this is a very important point, and I'm going to explain a little bit later more on that part. But this looks fine to me. We do have the correct flood list. So this should be ideally sent to remote VTEPs. Then the remote VTEPs, one of them should reply with the virtual MAC in response to the ARP request, right? So what we can do next is to do some packet capture from the remote VTEP side. And then we can see if we are actually receiving these broadcast ARP requests. And again, we're going to use TCP dump, and we're going to restart the test. And if we stop here the capture, we see that we indeed have broadcast messages encapsulated into VxLAN arriving at all of those VTEPs, right? So we have a broadcast arriving here on VTEP 1 with its VTEP IP as destination IP in the outer header. So this is part of the flood list, so that's what we expect. We also have the same thing from VTEP 2 side and same thing from VTEP 3. So why we are not seeing a reply then? The ARP request is getting to where it needs to get. All of those 3 devices are actually capable of doing routing. They have the Anycast IP and they have the VMAC configured. The problem here is due to the fact that we do see those copies sent to the VTEP IPs in the outer header destination IP. However, we are missing the copy that is supposed to be sent to the virtual VTEP IP. So that IP 10.10.10.10, we are actually also expecting a copy of this ARP request being encapsulated into a VxLAN packet with that IP as destination. So if you look at the show interface VxLAN 1 output from the remote VTEPs here, 1 to 3, we see that they do have the virtual VTEP configured. So they are configured with the virtual VTEP 10.10.10.10. And so this should be correctly, at least from their side, they should be working properly. And we can even see that this actual IP, the way it's configured is by setting the secondary IP into here under the loopback that is used for VxLAN. So the primary IP will be the VTEP IP, and the secondary IP is going to be the virtual VTEP IP. And of course, if you are intending to receive traffic, that's the destination is the virtual VTEP IP. We definitely need to make sure that the rest of the network knows that we have this IP. And we are doing that through BGP, as you can see here, show IP BGP. We see our BGP table, and we see 10.10.10.10 being advertised towards the underlay. So all the rest of the network is supposed to be learning this 10.10.10.10 address coming from all the 3 VTEPs that we have. At this point, I'll go back to VTEP 4, and I want to see if we are actually able to get to 10.10.10.10. And I can check my routing table here. And here is where we actually find something that is not supposed to be there. So essentially, here we can see the 10.10.10.10 address actually is configured as part of our loopback 0 here. So this means that we have, instead of having this route being learned through BGP, going through the network here up to the remote VTEPs, we are actually having these directly connected routes. So VTEP 4, once it gets that initial ARP request for the VMAC that needs to be sent VxLAN encapsulated towards the L3 VTEPs, it's actually not sending it at all. So this copy is being consumed locally, but this VTEP doesn't have the proper configuration for any cast gateway. So it doesn't have the VIP, it doesn't have the VMAC. So this just breaks. It doesn't go anywhere. So obviously, the first thing we need to do is to check if this is indeed the case, and it is there. Configuration is there, unfortunately. So the fix is very simple. It's essentially just removing that. And it might seem to be kind of a silly problem, but it's actually very common because a lot of times we're going to have templates that are applied to different VTEPs, but it's very important to have different templates for layer 2 only VTEPs and also layer 3 VTEPs, so we don't end up with such a problem like that. So here, resolution, just remove the IP address. Of course, make sure you remove the right one, otherwise you're going to break other things. And if we repeat the test, we can again run TCP dump using the monitor session, and we're going to try to ping the host in an external network again. And if you look closely here, now the packet capture on VTEP 2, we do see a copy of this VxLAN encapsulated ARP request trying to find the MAC address of the Anycast gateway. And we actually see 2 copies. We see the one that we saw before, that destination IP in the outer header is the VTEP IP. But now we also see the destination IP header here in the outer header, destination IP being the VTEP IP. So again, all the VTEPs, they received their own copy towards their own VTEP IP, but one of them end up receiving this copy. And when you configure virtual VTEP on a layer 3 VTEP, it's implied there is a rule as part of EOS that knows that once VTEP is configured, you're going to only reply to this VxLAN encapsulated ARP request for the VMAC if you receive a copy with destination IP in the outer header being your VTEP IP. The other ones won't be replied to. So that's how we can ensure that we don't have duplicated ARP replies being sent back to VTEP 4 and to host 4. Otherwise, you're going to see, well, it really depends on your scenario. There are many variations of problems you might see, but one of the most common problems would be MAC address flapping. So the VMAC will show sometimes as coming behind 1111, 2222, or 3223. So if there is no VTEP configured at all, you might see this MAC flapping behavior. So the VTEP comes to address this and ensure that we have a very consistent reply, just one reply back to the source that initiated the communication. So now if we take a look again, we can ping once again just to confirm some more packets. And we'll see that now we do have communication with our gateway, and we can ping the destination host without any issues, and we are getting replies, no problem at all. And the other thing we can check is the VxLAN address table on VTEP 4 side. So you can see that now we do have the virtual MAC here. And when you look at the remote VTEP, it's interesting because that's why the name virtual VTEP makes sense. Because from the perspective of this VTEP 4, it just learns that the VMAC is behind the VTEP IP. It doesn't care whether or not this is VTEP 1, 2, or 3. It just sees this MAC address behind this remote VTEP, and that's it. So it's very simple. It will always be this virtual VTEP, no matter which actual switch replies to the message. And well, the last thing is to check that indeed now we do have ARP entry in the ARP cache in the host side. So everything is good. There will be no, we have the MAC address learning, so there is no flooding, no problem at all. And the last thing I want to show is just from the underlay perspective, how things look like in case it's not clear yet. So we have spine 1 and 2 on the top of the screen and VTEP 4 on the right-hand side. So basically what I want to demonstrate is if I do show interface VxLAN 1, for example, we do see that now we don't have the virtual VTEP IP on VTEP 4. That's good because we don't want this to be there. We want the VxLAN encapsulated ARP request to be sent to the remote VTEPs. So if we look at the show IP route output, we'll see that we are learning routes towards the VTEP IP. And we actually have two different next hops and two different interfaces that can be used. So we have ECMP towards our destination. So we can use either the path through spine 1 or the path through spine 2. That's very common in data center networks. So we are going to have load balancing between those two links. And if we look from the perspective of the spine layer, we can do a similar check. And we see that here we also have an ECMP route with 3 different options. And those options are essentially just VTEP 1, 2, and 3. So we can choose whether any of them based on the load balance algorithm and the hash calculation that is going to be done based on the packet headers. So depending on the packet headers, how the packet headers look like, the devices are going to do the hash calculation and choose one of the interfaces to forward the packet to. And if we do a test, we can actually open here the remote VTEPs, and we can again run our packet capture. And we're going to see that if you do a ping from VTEP 4, you can ping 10, 10, 10, 10. And in this case, you can see that VTEP 2 ended up receiving the traffic. And the source here is 10454, which is my interface between VTEP 4 and spine 1. So we know the packet ended up being forwarded through these interfaces towards spine 1. And once it arrived on spine 1, we took the interface here towards VTEP 2. However, I can do another test changing some of the characteristics of the flow, the packet headers, by specifying the loopback 0 as my source address. And you can see that now the traffic was actually sent to VTEP 1 instead. So this is great and by design, because what we want here is to have load balancing between those VTEPs. So this ensures we have even load balance throughout the network in case you have to communicate with your gateway. So yeah, basically in summary, The issue here was that the layer 3 communication from our two hosts connected to this new layer 2 VTEP was failing because there was no connectivity to the default gateway. The host gateway was the Anycast gateway shared by all remote VTEPs, but the host behind this layer 2 VTEP couldn't learn this VMAC associated with the virtual IP. And this is because we have this special ARP handling when we are trying to figure out the virtual MAC associated to virtual IP. There is a requirement of this special handling using the virtual VTEP, so we can ensure that only one ARP reply will be sent back to the source. And this is done essentially by EOS replying only to the VxLAN encapsulated ARP request for the virtual MAC if the outer header destination IP is the virtual VTEP IP. So since the layer 2 VTEP was misconfigured at the beginning and had the virtual VTEP IP, then this copy was never sent towards the remote VTEP, and of course there will be no reply. By removing the virtual VTEP from the layer 2 VTEP, we managed to solve this issue. So now the layer 2 VTEP was able to send the proper ARP request encapsulated into VxLAN and get the response back from whatever VTEP had the virtual VTEP and received the traffic. This was based on the underlay routing, essentially. And also, after the ARP reply was sent, then we saw everything working fine. VMAC was learned from the perspective of the layer 2 VTEP. We saw the VMAC coming from the virtual VTEP. And from the host side, we saw now we have a MAC associated with our gateway. And some other points to keep in mind, just, very good to try every time you have an environment, try to get familiar with the environment as much as possible and confirm, for example, which devices are supposed to be doing only bridging or also routing. So we can speed up your troubleshooting. You can also make sure that you have all the best practices recommended, the recommended configurations are applied, and so we don't be in a situation where there might be some of the things missing, and sometimes you might not realize at the beginning, just after a while, and then this will make to pinpoint the root cause very difficult. And the last one is just to make sure you understand well how these Anycast gateway functionality and ECMP concepts are actually adopted as part of the VxLAN routing environment to prevent and also solve some of the problems. And with that, I think my part is completed. So thanks a lot for your time. I hope this was helpful. And now I'll hand it over to my colleague, Grant, who is going to be covering the troubleshooting part from the perspective of the CloudVision portal solution.
Thanks, Diogo. My name is Grant Bonds. I am a technical solutions engineer here at Arista Networks, and I'm specializing in CVP. Today, I'm going to be talking about the CloudVision portal side of this VxLAN troubleshooting. As Diego's gone over your CLI, this will primarily leverage CloudVision portal and all the great features it has to hopefully troubleshoot just effectively. All right. So looking at the topology, we're going to present our CloudVision portal troubleshooting guide as a simulated TAC case. Effectively, this allows us to leverage our advanced tools that CVP provides to solve this issue in a way that you might see when you're interacting with TAC. Specifically, we're going to hone in on problem statement 1 as the focus for this presentation. So Diogo's presentation 2 will be out of the scope of this specific guide. We may work on it in future CloudVision portal videos. As displayed, we have the same network as problem statement 1, including all the same spines, VTEPs, and hosts. However, in this case, we're simulating the addition of a new host on VTEP 3. That'll be host 3. So the problem statement effectively says that we have host 3 now that was just brought into the network, and it is receiving a lot of extra traffic that we do not expect in this current time. Once again, to scope the issue as well, we'll say that there's plenty of data between host 1 and host 2. Thinking back to Diogo's problem statement on number 1, we can think why this would be a nice scope to have. So the first thing we'll do in our troubleshooting journey on CVP is we'll verify that the traffic on Ethernet 5 on VTEP 3 is actually flowing as we expect. To obtain this information, we can go from the devices page and select VTEP 3. Then on the left-hand side, we'll select interfaces and Ethernet 5. When you click on that link, you'll see several pages on this image below that describe the interface. So we have interface counters, rates and counters, congestion tags, and our 802.1x description. In this case, we're going to be honing in on rates and counters, and we can observe that the Ethernet 5 traffic down to host 3 has no return traffic. So in this case, we're seeing about 18.729 megabits per second flowing over the time span of this specific window. For further troubleshooting, we're actually going to leverage a traditional PCAP in complement to CVP, and that'll help us get some more information similar to the more traditional troubleshooting methods that Diogo just went over. So we can see based on this PCAP, we have an IC&P echo reply from our standard flow from 10.0.0.1 to 20.0.0.2. If you remember back to your topology, that is host 1 and host 2. We can see from that packet capture, if we do it on the VTEP, which is Ethernet 49, that's facing towards the spine, we can see we have our encapsulated packet with the 2 VTEP IP addresses. Then if we drill down a little bit, specifically looking to host 3, we can see we have the 2 MACs, 97.1b and 8A59, with our flow from 20.0.0.2 to 10.0.0.1. So from here, what we can do is we can actually use CloudVision Portal to investigate the MAC addresses and IP addresses involved in this flow without having to go through a third-party system. All right. So when searching through MACs or IP addresses, there's no need to memorize a network or go through a complicated tool. We have something built into CVP for you to use. This tool is called Endpoint Search, and Endpoint Search can be accessed in several ways. The first thing we can do is access on any MAC or IP address that has a link on it in most of your CVP data tables that list any types of MACs or IP address. If you click on that link, it'll put you directly into that entry in Endpoint Search, as we'll see in the following slides. You can also use the search icon at the top menu bar of CVP and search for Endpoint Search to get to that main page. All right, so this is just a brief video demo describing the steps necessary to navigate to the Endpoint Search from various places in CVP. We'll go over the actual content of the page on the next slide, so don't worry about reading them now. Go ahead and set this to 1080p. There we go. All right, so we'll go to the devices page, select VTEP 1, then navigate to the left panel on switching MAC address table. We'll hover over any MAC address that has a link and click it. This brings us directly to that endpoint search for that MAC address, and we can see useful information on the MAC, including IP, or if available, a host name. We can then use a search bar, the top right-hand corner, copy a new MAC address in to find the other MAC address in this flow. We'll cover this page in depth on the next slide, considering everything that it has on it. In addition, we can use the top global search bar to search for endpoint search, or simply just type in the MAC IP to get to that same page. So you see at the very top, click there. And in this case, I can search for endpoint, or I can just paste in the MAC directly to get to the exact same page I was at. All right. Now, looking deeper into that results page, we can actually see a full list of occurrences for this MAC or IP address. The top card in this list will describe the device's role. In this case, we can see the device is in CVP's inventory and is actively streaming. So for devices that are not in CVP, we'll see any information gathered about the device from something like LLDP, if it's a neighbor to a streaming device, or any third-party streaming agents, if it's a third-party device streaming to CVP. This card generally includes things like relevant IP addresses, the host name, and the device status in inventory if available. The cards below will describe the instances of the MAC or IP address found in this network. In this case, it's most likely learned location is on VTEP2 because the MAC address is of VTEP2 itself. It's your statically defined switch MAC address. If you're interested in other potentially less relevant locations, you can click on the Show All Locations button link at the bottom of the page, and that'll expand out several more locations. This button ends up being particularly helpful if you're trying to trace down a lesser known MAC or IP address through your network to see where it may have been distributed. So putting all the pages together that we've seen so far, we can see that our MAC address 8859 corresponds to 10.0.0.1. Since it's just a device that is a neighbor to one of our streaming devices, we aren't streaming the host name, but we know based on topology that that device is host 1. The MAC address ending in 97.1b is in our VTEP, specifically in this case VTEP2, and we can see all of the information about that device since we are actively streaming it to CVP. Now that we've properly analyzed the flow and the players in that flow, we can ask ourselves the question, why are we actually getting this flow to this switch? In this case, it'd be host 3. So in this case, we'll follow Diego's same line of troubleshooting that we expect host 1 and host 2 to communicate, but we actually have data replicated from VTEP1. And as Diego mentioned more in depth, this can occur when we have an ARP binding, but no MAC in the MAC address table. So with CVP, we can actually confirm this historically. So what we'll do is we'll perform a network rewind and view the state in the past to confirm that this is indeed the problem. One of the primary strengths of CloudVision Portal is its access to historical data. So with this historical data, we can arbitrarily rewind the entire network to a known time and then perform in-depth analysis at that time. Note that by default, CVP's data retention policy is 90 days or 43,200 records per data path. That number seems a bit odd, but effectively that equates to a change per data path every 15 minutes for 3 months. So if nothing's flapping more than 15 minutes, we'll have the full 3 months. For specific data paths that are flapping extremely frequently, we may have less time in that data path just to preserve the integrity and the storage use across the cluster. So to move this time, we'll use the time window at the bottom of really any page with version data. So we can see here the specific time window has 3 primary sections. I want to go over here before we see how to use it on the next slide. The first one is a zoom in, zoom out button. That'll allow you to both zoom in to decrease the amount of time per pip and zoom out to increase the amount of time per pip. The calendar time selector, if you click that, sometimes it says now. If you're looking at the live view as well, it'll pull the calendar view that you can select the date time from. And finally, you can see on the right-hand side, or in this case, it's on the right-hand side since we have it dragged there, it is our selected time. So this describes the current state of the network at the time that you've selected. We also have a live button. So if you want to just follow the newest data coming in, you can always click that live button and it'll continually update as the data is streamed to CVP. And so this will be a brief demo describing how to interact with our time window. We'll go ahead and get this played up here. All right, so to demonstrate the time window functionality, we'll once again navigate to the same table. We'll go to switching MAC address. Once there, we're going to locate the bar at the bottom of the page. Note that there are currently 15 minutes between time pips. So by clicking on the zoom in button, we can see that there are less time between the pips. By clicking the zoom out button, we have more time between the pips. So we can see more time per scope. By clicking on the now or the time button, we can look at a calendar view. And by clicking at that specific time, we can really drill down to the minute, hour, and second for any time we want to hone in on. We can then select and drag our current time as well. In this case, we're going to drag it to a specific network time. And we can see at that specific time, we have the MAC address in question of our host on the VTEP. So we see we have that 4A89. However, when we want to go back to live, what we can do is we can select live, and we no longer have that 4A89 demonstrating that it indeed has changed over this period of time that we're seeing the issue. So now we're looking at the live view. This is just a static image. We can see that VTEP1 specifically is missing host 2's MAC, and VTEP2 is then missing host 1's MAC. Note that these are both sorted by dynamic, so we have more MAC addresses in play, but you can sort any of these tables by any value. So we just did this to decrease the amount of MACs shown. Once again, we can scrub through that timeline, and we can see that a change did occur a few hours ago where we had that ARP timer reset and the MAC addresses were then relearned. Specifically here, all we're demonstrating is we have those addresses that are learned locally on the interfaces learned over the VxLAN 1 interface on their respective VTEP. So instead of scrubbing through the timeline, we can also do a direct comparison of the addresses. So at both of those tables, you can note there are quick access buttons at the top of most data tables that'll navigate us to the device comparisons window. This specific window we went over a bit in one of our first webinars. It describes the ability to compare both the state of the device at 2 different times or the state of 2 different devices at 2 different times. So effectively, we can do really fine-grained control to look at specific metrics for several different types of comparison operations. Specifically, in this case, we're interested in looking at the differences of the MAC address across the VTEP during the time period where we're seeing the issue versus the time period where we're not seeing the issue. So in this case, we've located and identified that there is a time period that is okay, we're not seeing the issue, and we've located the current time, which we are currently seeing the issue. And in this case, when we compare the same VTEP1 at those 2 times, we can see that as expected, the IP address of, or sorry, the MAC address of our host has actually been removed from the MAC address table. So in summary, this Cloud Vision portal really offers advanced troubleshooting techniques that complement your traditional network troubleshooting and enhance the overall troubleshooting experience to give you fine-grained control over both time and over your network state. We can utilize that ability to arbitrarily rewind our network state to trace issues back to their inception and provide really advanced root cause analysis that allow us to do full network tracebacks during an arbitrary time. And finally, we can leverage our MAC IP searching to quickly identify switch mappings without having to scroll through third parties or look through other systems that may be a lot slower. And with that, that is my portion. I'll go ahead and turn it over to Loki. Thank you so much for attending.
Thank you, Grant. Let's move on to the next slide, please. Okay, cool, perfect. So thank you, Diogo, and thank you, Grant, for your outstanding delivery and comprehensive deep dive on VxLAN during this session. This has truly been a technical treat for all of us, and we sincerely hope that all of our customers found this session incredibly valuable. Recording for this session again will be available on the Arista community page along with the presentation material and the questions what we covered from the technical lead side. Our next session, session 6, that will be last for the quarter 2, is scheduled on 28th of June at 11 a.m. Eastern, which is going to be an extension of the VxLAN routing, and we highly recommend everyone to attend that. And in order to continuously improve and cater to your needs, we do actually have a short feedback form, and we kindly request everyone to participate in that. The form is actually shared in the chat. It's a Google form, and it has around 3 to 4 questions. So your feedback is immensely valuable to us, and we'll definitely plan to incorporate it in our future sessions to ensure more enriching experience for all our customers. So I definitely request everyone to please provide your feedback using that Google form link. And at this point, we are going to keep the webinar open to answer any questions what you may have. You can use the Q&A manager to ask our panelists any questions at this point.
think we have a question. I can actually answer that live.
Yes, please, Grant.
Yeah, so we can't do any provisioning of third-party devices, but we often do streaming of those devices. So we have some guides online as well that we can talk about the specifics of what we allow. Generally, you can stream through things like SNMP and Open Connect or OpenFlow. For third-party devices, we have some tested, but we do support that in a limited fashion, yes. But no provisioning, unfortunately.
Okay, cool, perfect.
Open config, my bad. Thank you.
Awesome. Appreciate the feedback about the session from everyone. Again, I'll request everyone to actually use that Google form link to provide the feedback. We definitely want to incorporate that feedback for our upcoming sessions and want to make it better for our customers. So, okay. If there are no other questions, then we are going to wrap this up. Thank you, everyone, for joining us today. We really appreciate your time, and we hope that you enjoyed this session as much as we enjoyed putting this together for you. So thank you, and have a wonderful day ahead. Thanks, guys.